In this video, we continue our look at evaluating limits algebraically. And we've seen previously where evaluating a limit using algebra boils down to simply evaluating the function, right? Now we're going to look at a few problems where it's a little bit more in depth and there are a few more subtleties to keep in mind. So let's take a look at look at this limit. So let's consider the limit x as x approaches 4 of x minus 4 over x squared minus 16. So let's take a look at that particular limit, right? This function is one of those elementary functions that we previously evaluated, and we evaluated by substituting. But let me remind you, and sometimes when you get into the habit of substituting, you lose sight of those algebraic properties that we've talked about. And what happens is, in this case, we can try to take the limit of the numerator and then divide that by the limit of the denominator. All right. But if you notice, something interesting happens. The limit of the numerator, that's equal to, again, if we use our process of just evaluating 4 minus 4, which is 0, and the limit of the denominator is 4 squared minus 16, which is also 0. So when we evaluate the top and the bottom separately, we get 0 and 0. But then look at what the function says that we're supposed to do. We're supposed to divide. So does that mean the answer is 0 over 0? Right? What is that? How do we make sense of that? Well, it turns out, we know we can't divide by 0. But then to also have a 0 on the top adds an extra bit of subtlety. And this expression, in the context of a limit, is said to be indeterminate. So if a limit results in the form, and again, I always put this in quotes because it doesn't mean anything, right? It's meaningless. In fact, that's why we use the word indeterminate to describe it. So if a limit results in the form 0 over 0, meaning, and the way we interpret this shorthand notation is that the top approaches 0 and the bottom approaches 0, we say the limit is indeterminate. Right, so it's an indeterminate limit. And does that mean that we stop? No, in fact, we never stop at 0 over 0. The rule is, so algebraically, what we try to do is to reduce the function to its simplest form and then try to re-evaluate again. So in this case, we're going to use algebra. Oh, can't spell algebra there. So we're going to use algebra to reduce the function to its lowest or most reduced form. And then try to reevaluate. So, and then reevaluate. In other words, try to plug the number back in again. So when we plugged in the 4, we got this weird 0 over 0 form, which doesn't mean anything. But then we look closely at the function and see if it can be reduced. So let's try that, right? And again, this is where all those wonderful tricks from algebra are going to be helpful. So remember, the limit was as x approaches 4, and the function is x minus 4 over x squared minus 16. Now, as far as reducing this, this is a rational function, and one of the things that you want to try is to factor and reduce, right? You very rarely do you hear me use the word cancel, because it sometimes sends the wrong message. But what we want to be able to do is completely factor and completely reduce this rational function. And if I look closely in the denominator, I have a difference of 2 squares, right? And notice how I'm using the limit notation, because all I'm doing is I'm going to first focus on simplifying or reducing this function, and then at the end I still have the limit to compute. So it's very important that you continue to use the correct notation. The only time that you are allowed to drop the limit is pretty much at the very end, when you are just about to evaluate, or you have evaluated and you've gotten your number. But here in the bottom, is there a difference of 2 squares? So the x squared minus 16, it factors as the product of x plus 4 and x minus 4. And then this is where we can reduce, because we see there's a common factor of x minus 4. Right? So once we have a common factor, that's what allows us to reduce this. And what are we left with? Well, in the numerator, there we can always put a factor of 1. So there's a 1 left. And then in the denominator, oh, wait, I think I canceled out the wrong factor here. That wouldn't be good. Let me fix this. So this is x plus 4. It's the other factor that goes, right, the x minus 4. So then the limit of x as x approaches 4, what are we left with? 1 over x plus 4. Now, again, this is a rational function, and this is where I try to plug my 4 back in. And lo and behold, I don't get some weird 0 over 0 now. I get an actual number. So the numerator is a constant, and we know the limit of a constant is a constant. And then the limit of the denominator, it's a linear function, a polynomial, so I can just plug 4 in, and it's 4 plus 4. So that function approaches 1/8. So originally, we ended up having a 0 over 0 form, because the limit of the numerator and the limit of the denominator are both 0. But then the property of the function allowed me to factor and reduce, right? So the property of that particular polynomial, it's a difference of 2 squares. I could factor and reduce, and then I get my limit, all right? So let's do a few more examples of different types of, I would say, tricks from algebra that we might have to use. And again, I say tricks, not that it's something there's anything bad with it. No, it's just or think of it as a set of tools, right? And you try them in different instances. So let's look at maybe 2 or 3 more examples. And let's start with another rational one. So let's take the limit as x approaches -3 of 2x squared plus 5x minus 3 over 4x squared plus 17x plus 15. Okay, so what I'm going to try to do on the side, I'm going to try to see, well, what do I get if I take the limit of the numerator separately? And then what am I going to get if I take the limit of the denominator separately? So 4x squared plus 17x plus 15. Now let's see. So for the first limit, we're going to square this -3, so that becomes a positive 9 times 2. So that's 18. And then we have a minus 15 in the middle, and then a minus 3. So that's equal to 0. So the numerator evaluates to 0. What about the denominator? Let's see. Again, -3 squared is 9 times 4, so that is 36. And then 17 times -3, that's -51. And then plus 15, and shockingly, you get another 0. So this is our indeterminate form. And again, I'll keep saying it, we never stop at this, because 0 over 0 means nothing, right? In the context of these limits. So now the question is, can this be factored? Can it be reduced? Now, I want to remind you of a very useful property of polynomials. Remember, the numerator is a polynomial, the denominator is a polynomial, and when we plugged -3 into both of them, and that's what we did over here, we got a 0. Well, there is a factor theorem from algebra that tells us, and basically this is what it says. If f of x is a polynomial, right, and f of a is equal to 0. So if you plug a number into a polynomial and you get a 0, then x minus a has to be a factor of that polynomial. So is a factor of f of x. Well, what does that mean? Well, here we plugged -3 into both of these, so that it means x minus -3, which is the same as x plus 3, has to be a factor of both of these polynomials. So knowing that I have this 0 over 0 form, right, and I know the number that I plugged in, I know that the top has to have x plus 3 as a factor, and so does the bottom, right? All we have to then figure out is what the other factor is. So you kind of, you know essentially half of the factorization of each of these quadratics. Well, what is the other half? Well, and then this is where you can sort of balance it. If you look in the top, you need a leading term of 2x squared. So you'd need a 2x right there. And then you need a constant term of a -3. Well, here you have a plus 3. So the only way you could, when you FOIL it out, you could get a -3 there is by having a -1 there. And then you can check to see that the middle term works, right? And then similarly, you could factor the bottom. We need a 4x there, and then we need a plus 5 there, right? And that's the complete factorization of both the top and the bottom. So this factor theorem, right, which works for polynomials, right? You know, if you evaluate a polynomial and you get 0, then you automatically know one of its factors. You know, there's what this is saying, there's an important relationship between the root or 0 of a polynomial and its factorization, right? And then once we have this, we can reduce, we can see the x plus 3 in common, And so then this reduces to this limit. All right. And again, I also want to point out that this function is not the same as this function, right? It's just what happens is that they both have the same limit. So we can reduce the original to the simplified form and then try to evaluate again. And it's at this point where we're going to evaluate, and you can see when you plug -3 in, you're not going to get a 0 at the top or at the bottom. So I know this will be my numerical answer. So I will have 2 times -3 minus 1 over 4 times -3 plus 5. And that's -7 over, that's just -12 plus 5. So that's also -7. All right, it comes out to be 1, right? So that's our limit of this function as x approaches 1. I'm sorry, as x approaches -3, the function approaches 1. Let's do another example. And for this one, actually there are a couple we could do. Let's do one that involves work with fractions. So we have to work with a lot of fractions. So this one I'm going to use a different variable. I'm going to use h. And let's say this is 2 over 3h plus 1. And then minus 2. And then all over h. All right. So let's see what happens if we plug h equals 0 in. Well, or more precisely, if I take the limit of the numerator as h approaches 0. So we have 2 over 3h plus 1 minus 2. Well, plugging a 0 there gives me 1 in the denominator. And then so 2 over 1 is 2. And then minus another 2. So the top evaluates to 0. And then I think you can see the bottom, which only involves a factor of h. That one also approaches 0. So yes, this is another 0 over 0 form. Well, the way this is set up, it's not really ideal for factoring or reducing right now, right? And again, there are different ways we could do it. What I'm going to do is take the numerator and express the numerator as a single fraction with a common denominator. So let's do a little side work over here. Let's do 2 over, so we have over 3h plus 1 minus 2. If I put this as 2 over 1, then I can see that the common denominator is going to be the 3h plus 1. So 3h plus 1. This numerator stays. This numerator needs to be multiplied by 3h plus 1, right? So I'd have to multiply the top and the bottom here by 3h plus 1. So it looks like this. And then let's go ahead and simplify this numerator. And we end up with a -6h, so -6h. And then I end up with 2 minus 2. So the constant term cancels out, because here's a positive 2, and when I distribute that -2 to that positive 1, I get a -2. So this is my numerator, and then it's all over 3h plus 1. Right, so that's what the top simplifies to, right? So let me rewrite my limit now. So the limit as h approaches 0. So the top is -6h over 3h plus 1, but all of that is divided by h. So how does this work? Well, there are different ways. So, if you have a over b over c, that's the same as a over b c. Because you can think of it in sequence. You're you're dividing a by b and then by c. All right, so you could write this. So this is the limit as h approaches 0 of negative 6h over, this would be, in one of the denominators, one of the factors in the denominator, and then the h would be another one there. Right? But then when you do that, you can see that common factor right here. So it has a common factor of h. So that reduces. So now we can actually reduce it and get rid of that common factor. So negative 6 over the quantity 3h plus 1. And now let's try to evaluate. Well, the top is a constant. And the bottom, plug 0 in for h, you'll have 3 times 0 plus 1, so you end up having negative 6 over 3, which is equal to negative 2, right? So that is the limit of our, somewhat complicated looking function. It's complicated looking because you had a fraction within a larger fraction. But again, carefully going through our algebra, we again were able to reduce it to its lowest terms and then evaluate again. Right? So there are a couple examples that illustrate some of the little tricks from algebra that are very, very useful. And in the next video, we'll continue to look at a couple examples and remind you of different things from algebra that can help us evaluate these strange 0 over 0 forms.